Multi-stage compression, or simply the multi-staging. So initially, reciprocating piston compressors that are used in a cylinder to force air into a chamber, no? So where it is compressed, so that simply is compressor design. So the simple type of design, which is usually a single cylinder chamber, so that is a piston and an arrangement, no? So for straightforward, so this setup, so initially what we have done discussing previously, that those setup, so sa single stage, so they are limited in its efficiency and the capacity delivering the high volume of pressurized air. So that's why multi-staging compressions were introduced. So for higher requirement and to save efficiency of the system, so a multi-stage is being introduced to the system. Okay, so because it provides a better efficiency and also it saves power. So multi-stage compressors, it has a features of a series of cylinders. Usually we have two cylinders there. So one for the first stage and low stage, and we have for the high stage. So between each stage, the air passes through a heat exchanger. So later on, we'll show you that one. So we have an exchanger to cool down the air before you're going to compress to another stage. So the air is then forced into additional chamber which is pressurized to the extent. So sometimes they have not only a two-stage, sometimes in other industrial use they have a three-stage type or four-stage type of compressor. So for the benefits, so we have for using a multi-stage compression. So initially we have one which is to save power. Okay, so that means we have to improve, it improves the efficiency for a two-stage compressors. So it has a perform less work, so it means we save the power that will being supplied to an electric motor. So one sample we have here of a two-stage compressor is this one. So you will notice here we have here 1 and 2, you have two compressors. So it depends, no? So medyo magkamukha naman yata sila ng itsura, but you will notice here we have two cylinder piston, two cylinder sa baba and another two cylinder here, one setup of compressor here and one setup of compressor here. So there is typically, usually, so we have here, I think this is one is an heat exchanger to cool the air as it passes to the air to the second stage of compression, or it can be used also, then can be compressed also on the on this upper part of the compressor. Now this is saves the power. So later on we will see about makikita na, I will show you in the computation how we able to save power by using a multi-stage compressor. Then we have it also better reliability. So intercooling stage of two-stage compression, so creates a less chance of overheating. So limits the gas discharge to temperature. So less heating. So because we have tinatawag na we have an intercooling system, or intercooling system to cool down before you going to go to the second stage. So it has less moisture build up. So cold air has a lower moisture content. So moisture is compressed and air can lead to equipment failure and premature wear. So that is for maintenance. And also we have smaller footprint. So when we say smaller footprint, so you have only small size in installation in the area. Then limit the pressure differential per cylinder. Okay, so I just only limit how much pressure is being introduced to the system for each cylinder. I have here, I bring down here a simple diagram showing of the multi-staging compressor, how it works. So you have an inlet here during the suction stroke. You have your valve here, so air is entering here. Then it will be compressed. The airs will be compressed here, and then it will be discharged on this side. So air will be passing to an heat exchanger. So this is heat exchanger. So HX. So we have your heat exchanger here. So air is compressed. So alam naman natin na if we compress the air, so from your PBT relationship, it also increases the temperature. Now, as you increases temperature, it will be passing to the intercooler. So where the intercooler, so or let's say it is a radiator type or at a heat exchanger, so it cools down the air before another stage of suction here for the second stage or high pressure. The air will be compressed again, and air is compressed at a higher pressure. Now here we have the process of heat exchanger. Here we have a constant pressure at this side. So a constant pressure removal or heat removal of the air, then at lower temperature air is compressed again at a higher pressure, and with this discharge it has a higher pressure and also a lower temperature. Comparing from here, if we do not have an intercooler stage, then this produce a lower can produce a save power to the system. So now for the intercooler, so we can use for the intercooler, we can cool the intercooler by means of supplying here of H2O in, and you have our H2O out. Or we can use also by means of fan. So if you have your cooler here, so you have your grill just like an engine radiator, so you have your fan. So it can by means of heat transfer, you can cool also the air. So it depends on the system design. So we can use also water, and also we can use air by means of cooling the radiator or intercooler. Now I bring down here a piston in a cylinder arrangement. Now the fresh air entering here during the we call it the suction stroke. I'm gonna write here. We have your suction stroke towards here. So this is now our suction stroke. Okay. So I'm gonna change this one. So since it is suction, so I'm gonna change the rotation. So we have here rotation towards like this. So in order to have a suction stroke. Okay. Now I'm going to show you how to plot that one in a Power PB diagram. So you will notice here. So this is the top dead center. Now your bulb here. Okay. So the intake bulb. So we have your fresh air here. Fresh air entering this side. No. Then we're going to plot that one in a PB diagram. Okay, so this is our PB diagram. So this is how it looks like. Now, as the call this the connecting rod or the crankshaft continues to rotate, so the piston achieves. Now during the suction stroke, okay, so our piston moves down, so our crankshaft rotates. So, nag-ikot na yan. Then, our pistons move to the, so our piston moves to the bottom dead center from the top dead center. So, we have here your top dead center. Okay. So, what I'm doing now, I'll be predicting the volume of the air that is entering I'm predicting the volume of entering in the piston. Now, so hindi naman siya totally air is being as you move the piston, air is not being pulled this sucked 100%. So that's why nagkakaroon tayo ng volumetric efficiency. So there is a portion here. So I'm going to show you how ideally, no? So ideally, ideally, this is the profile o usually nangyayari, no? So this is only the air that is being introduced to the during the suction stroke. So it is not completely filled with air. So that is the nature nung ano, usually ganyan yung nangyayari. So it not that's why we have yung tinatawag na volumetric efficiency. So that is how much air that is being introduced sucked or introduced into the cylinder. So this is during the suction stroke. So if we're going to plot that one in our PV diagram, okay, so we will have here at this part, so this is now our tinatawag natin na call this is now our clearance at this time. So this will be our C or clearance. So usually hindi naman siya totally nakakarating doon sa taas, but ang top dead center mo, yeah, sorry class, I forgot, but this is the now our top dead center. So I'm gonna mark this one. Top dead center. So this is now our top dead center. So usually during the compression stroke o ang location ng piston mo is only at this point. So we have a clearance. In order to provide yung tawag dito space for the valves, for the movement of valves for open to close. So para maiwasan yung clashing of the valves, suction valves and exhaust valves. So maiiwasan siya by providing a clearance on the duct dead center. Then we have here your point 1 at this part, no? Now, as it reaches at the bottom center, so during the suction stroke, after that, the bulb of the suction stroke will be closed. So, and we have only this part of volume of air that is being sucked inside the cylinder. So the valve is closed. So the air is contained inside the cylinder. I forgot to add yung exhaust valve natin dito. So during the, I'm going to explain it again. So during the suction stroke, our exhaust valve is closed. Okay. And when the suction valve is closed, and that is the time that the compression stroke will be start, and still our exhaust valve is still closed, and you will notice here that there is still a space that which do not have a fresh air from during the suction. So the air is not fully the air is not fully occupy the volume or let's say the space of the cylinder. So that's not, hindi siya totally punong-puno, but there is a still space, the white space here, so provides that there is no air at this side, but only this is the air that is being sucked during the suction stroke. Notice here, now we have yung tinatawag na compression stroke. So we have now yung compression stroke. So if you're going to plot that one in our PV diagram, okay, so we have here going there. So you will notice also that our exhaust valve is still closed also during the compression. So that is the PB raised to N called C. Now, plotting that one in our PB diagram, starting from point 1, bottom dead center, to the compression state. So we have here now your PBN raised to N, which is now your constant polytropic. We're starting now the polytropic compression. And the heat at the cylinder, okay. So we have heat rejected already. Just the buildup of heat inside the cylinder is starting, and we have to, and those yung heat that is absorbed by the wall of the cylinder. Now, during the compression stroke, as the piston reaches at the top dead center, okay, so still we have the exhaust valve and your suction valve are still in closed position. And if we're going to plot that one in our PV diagram, so from 1, so we have here your point 2 at this side. So this is now your top dead center. So the pressure here, we have the high pressure side at this side. Okay. And an air pin, this one. So we have the air pin. So air pin is introduced the wall of the cylinder to further the heat transfer or to cool down the wall of the cylinder due to polytropic compression. At this stage, so when we compress the air, so air is being exhaust, the exhaust valve is open and the air is going out. So sometimes this is also called a delivery valve. So if you're going to plot that one in the PV diagram, so we have here your point 3 at this side. So this is now our point 3. Okay, this one. Okay. So this is our point 3. So that will be going out from the cylinder compression. Okay. So that is the air that is being going out at a high pressure. Then during the suction stroke again for the next cycle, so we have here the the flow or the flow of air or flow of the volume here. So this is the pattern of the PV diagram going down here. Now this is now again the suction stroke. So we have here your point 4. So as the first stage compressor discharge, no, discharge to the first stage compressor, so the air is being cooled by a jacket water by means of a circulating pump. So we have a jacket water in, and we have here your jacket water going out. Then as we cool the temperature of the air, it is being sucked by another compressor, then it will be compressed it into a higher pressure at this point. So that is the use of the multi-staging of the so that demonstrates the multi-staging of a compressor. So you will notice here we have a little amount of work here under the PB behind the PB diagram. But it is a common practice that it is the operation of the multi-stage compressor are adjusted, okay, to approximately they will have an equal amount of work done in the cylinder. So a practice that will result the minimum work of the compressor given the quantity of the gas. Okay. Now for the work, so that will be equal to the work of the low pressure cylinder and plus. So I need to move this one. So that will be plus the work of the uh, high high pressure cylinder. So that will be the corresponding work of the system. Now we have for the work of the low pressure, so we have your N, okay? So we have your mass flow rate, then multiply by the R, T sub 1, and it is divided by the 1 minus your N. Okay. Then we have the ratio of pressure 1 to pressure 2 over pressure 1 raised to the power of N minus 1 over N minus 1. Then plus again N. We have the mass flow rate. We have your R, and we have temperature 3. Okay. So at the point 3. Then so this is already the discharge. So delivery bulbs already of the discharge of the first stage compressor, then it is divided by again by 1 minus your N. So again the ratio of that will be the P4 minus your P3. So that will be on the upper part, P4 over P3, which is raised to the power of N minus 1 over N minus 1. Okay. So P4 to P3. Okay, so that is the ratio. So since we have during the suction stage, so that will be the suction uh of the first discharge. So usually that will be the discharge, no? So P3 and P2 are commonly equal there. So if you going okay, so since we're going to adjust this one, so usually, in actual, it will be adjusted in order to have. So later on, I will show you that. Lately I'm going to demonstrate that one. So now, what we have here is that your P2, okay, is equal now to your P3. Okay. So then we're gonna call this one your P2 and P3 at this point are equal pressure. So we're gonna call this one as your PX. We're gonna name this one as a PX. So we have the work at the load stage, so we can, and also our temperature 1. Okay, so we have your T1 there, so our T1 will be equal now to your T3 since we been have an intercooling here. So from here, discharge, which is your point 3, then going back to this one, so we be lowering the temperature during the suction stage of the compressor. So that's why your T1 and T3 are equal. So we lower the temperature. So that will be constant pressure heat rejection at that point. Then we can rewrite our equation of your work. So we can rewrite that as your work, that will be your N mass flow rate. We have your R, T sub 1, then divided by your 1 minus your N. So we have here, so P2, which is equal to Px. So I'm going to write here Px over P sub 1 raised to N minus 1 over N will be minus 1. Then plus, this will be N mass flow rate. We have your R T3 divided by 1 minus N. Then we're going to multiply this with your P4 but then the value of your P3, which your P3 is equal to Px also. So that will be raised to N minus 1 over N minus 1. Okay. Since we have the work which is being equal to the high stage and to the low stage compressor, so we can rewrite our equation. We can equate this one as your N mass flow rate. We have your R T sub 1 divided by your 1 minus your N. and this is multiply to the ratio of your px over the p sub 1, then it is raised to n minus 1 over n. So this is minus 1, okay? So I'm gonna move this one here. Then this is now equal to the work at the high stage compressor. So we have again, so mass flow rate, we have your R and P3 divided by your 1 minus your N. And it will be multiplied to your P4 over your PX, which is raised to N minus 1 over N. This is 1 also. So we need to cancel what is common here. So this one is cancelled. So we have the same mass flow rate, and this one is also cancelled. Your R is the same. We have the R. T sub 1 and T sub 3 are also equal. Okay, cancel that one. So what is left now? We have your Px of the P sub 1, which is raised to N minus 1 over N minus 1, is equal to your P4 and Px that would be raised to N minus 1 over N. Okay, 1 minus 1. So if we transfer the negative 1 to the other side, so it will be cancelled out, it will be 0 out. And we have the common exponent, so this one will be cancelled. Then it can be now equal now your Px over your P sub 1 is equal to P sub 4 over your P sub x. Cross multiplying that one, so we have your Px square will be your P4 times your P sub 1. Or let's say the Px now is equal to the square root of P sub 4 times your P sub 1. So this one, your Vx, represent as the intermediate pressure for the minimum work. So since we have your work of your compressor at the low stage is equal now to your work at the high pressure stage. So we can rewrite our equation as that the work at the low stage is the work now, total work of the system can be equal to 2 times the work of the low stage compressor, or it is also equal to 2 times the work at the high stage of the compressor. So we can write our equation that will be 2 times your N mass flow rate times your R T sub 1 divided by 1 minus N. Then it is again substitute that one, we have your Px over your, or let's say we don't use the Px here, but we use the work at the low compressor since we are equal now. So we can use P sub 2, P sub 1, we have your N minus 1 over N, we have 1. Okay, then it's also equal to your 2 times your N mass flow rate. Then we have your R times your T3 divided by 1 minus your N. Okay, so then gonna multiply that one to P4, the ratio from low to high. Then we have your N minus 1 over N divided by. So this is, sorry, this will be 2N or N, okay, so minus 1. Okay, so we have the work now of the multi-stage compressor. Now, for a pressure drop in the intercooler or the heat exchanger, could be spread on each side of the value. So we have your P2, so that will be your Px, plus now we have your pressure drop. So we can spread those pressure drop on the side, on those both sides, so that will be divided by 2. So for your P3, so this is for your P3, we have your Px, that will be minus your pressure drop, then it will be divided by your 2 again. So for the heat rejected in the intercooler or the heat exchanger, so we have your Q. Okay, so that will be or on the or the jacket water that will be used to cool down the intercooling. So we have Q in the intercooler is equal to the mass flow rate of your air, mass flow rate. Okay, then we have this specific heat at constant pressure. Then we have your T3 minus your T sub 2. Well, I forgot this one since we are in the multi-stage now. So I'm gonna change this point 4 since it is multi-staging already. So we have here our point 4 at that stage. Okay.